Hi, my name's Jeremy Orme and I'm a software architect from Connective Logic, and today we're going to look at the benefits of adopting a parallel first approach to creating new applications and migrating legacy applications, and how our Blueprint toolset enables you to do that. So there's two different ways you can approach parallel programming: bottom up or top down, and we're going to consider the bottom up approach first. We call this serial first, parallel later, and that's because you write your program serially to begin with, or you start with an existing serial program, and then you identify the parts that you can parallelize, such as loops, and then you introduce parallel constructs. So the parallelism comes in right at the end, and those parallel constructs could be loop parallelization, or it could be opportunistic task scheduling. So you can find something that you can execute asynchronously and you can create a task for that, and then at some later point you can wait for that to complete. An example of this is futures, and this is typically what most technologies around today are using. Some examples are Microsoft's Task Parallel Library, Intel's threading building blocks, and the Silk language from Silk Arts. This tends to be a very fine-grained approach, and what I mean by that is that the jobs that are being scheduled are very small. The alternative approach, and the one that Blueprint takes, is top-down, and we call this parallel first, serial later, and that's because you're thinking parallel straight away and the serial part is introduced at the end. So the process is that you take your existing sequential application and you analyse that, and from that analysis you can then produce a parallel top-level infrastructure. If it was a new application, you could go straight to that step. Producing that parallel top-level infrastructure consists of creating or reusing top-level components, so you can just drag them on from an existing component palette, or alternatively, if they don't exist, then you can create new definitions and populate those. And in the case where you do create new definitions, then you might want to break those down further into subcomponents. And each time you break down a component, you're introducing more and more concurrency, and quickly you get to the point where you don't actually need any more concurrency, and the best thing to do is to just call into a piece of sequential code. And it turns out that those pieces of sequential code can actually be quite large, so most of your original sequential code remains unchanged. So the parallel first approach tends to be coarse-grained, and another important point here is that top-down decomposition is accepted good practice for sequential programs, so we don't want to take a step backwards just because we've got to deal with the problem of parallel hardware. James Reinders is also promoting a parallel first approach. At this point, I'd just like to introduce the tool and show you what some Blueprint components actually look like. This is the top-level circuit for our sonar example, and you can see that this consists of a number of subcomponents that have been connected together. If we double-click on any one of these subcomponents, we get taken to the corresponding definition, and this particular definition itself contains a subcomponent, so we can double click on that and get taken to its definition. This definition doesn't instantiate any subcomponents, and so it just calls sequential code. So in this particular case, when the events arrive on both of these connections for this object, the sequential code that it contains is going to run, and if we double click on this, we can look at that sequential code. Notice that this object has a dimensionality. That's the NB in the square brackets, and what that means is that we can have NB distinct versions of this code running in parallel. So even though this definition doesn't contain any subcomponents, it still has a high concurrency. By nesting subcomponents like this, you can see that you can introduce very high concurrencies very quickly. Component definitions like the ones you've just seen contain sequential code within the rammed method objects, but they also program the synchronization between the sequential code. I'm just going to show you a quick example. Here's the classifier circuit from our sonar example, and in here we've got this object which is called a collector, and what this does is it collects these two events, and when they've both arrived it propagates them on as a single compound event. And we have a number of objects like this that perform different functions and allow you to synchronize the behavior of your application. The fully parallel nature of these definitions means that you can program any piece of sequential code to run as a result of any combination of other events. So you're not just restricted to data parallel constructs like loops. Blueprint components are fully encapsulated and prototyped, so you don't have to worry about what's going on inside of them. You can just join them up, provided that the prototypes match, of course. They're autonomously executing, and what we mean by that is that they will distribute themselves across the available processing hardware, so you don't have to worry about any of that stuff. And also, just as importantly, it doesn't matter how many of these components you create and plug together, all of them will run within a pre-specified number of threads that's specified within the process definition. And in fact, you can run your entire application in a single thread, which is very useful for debugging. All you have to do is change a number. Blueprint objects exchange information using an optimal scheme for the architecture. What this means is that if two objects are co-located in the same process, then they're going to exchange information using reference. If they're separated across a network, then they will use message passing. This is determined transparently at runtime, and the programmer never has to worry about it. This is a very important point given that the SMP architecture's days could be numbered, but I'll come back to that later. Blueprint component definitions are logical descriptions. They don't assume any particular topology, and they can be accreted to any number of physical processors. Okay, let's take a look at a simple example application that I'm going to use to illustrate my points. This is a simple matrix calculation. Firstly, a computation is done for each cell of the matrix, and then as rows and columns become available as the cell calculations complete, those rows and column calculations can be completed as well. And finally, when all of the rows and columns are done, then there's a single serial calculation at the end. Also, as soon as the rows and columns have completed, the next set of cells can begin processing. You can see in the bottom left corner there the TPL implementation for this problem, and here we've used parallel fors to do each of the processing stages, with just a synchronous call for the output stage at the end. And in the top right corner there you can see this processing chain represented. And so we do all the cells in one go, then all the rows, then all the columns, and then the output stage. Here we can see the blueprint solution to this problem. And straight away you can see that the rows and the columns can run in parallel, which we couldn't do with the TPL solution. And if you look up to the top right, we have a different representation for how this processing chain is going to work. And this is because the blueprint solution allows us to easily pipeline this chain. So the current iteration is overlapped with the previous iteration, and I'll go into the advantages that provides shortly.